Let's begin by exploring the basic concept of radioactivity. At its core, radioactivity is a natural process where unstable atomic nuclei release energy in the form of radiation. This phenomenon was first discovered in the late 19th century and has since become a cornerstone of modern science. Radioactivity can occur naturally, such as in elements like uranium, or be artificially induced in laboratories. Understanding radioactivity is crucial because it not only shapes our knowledge of atomic structure but also impacts various fields, from medicine to energy production. As we move forward, we'll see how this invisible force has shaped our world in unexpected ways. Story of radioactivity's discovery is both fascinating and inspiring. In 1896, French physicist Henri Becquerel stumbled upon radioactivity while investigating phosphorescent materials. He noticed that uranium salts emitted rays that could expose photographic plates, even without sunlight. This accidental discovery paved the way for further research by scientists like Marie and Pierre Curie, who isolated new radioactive elements. Their pioneering work not only expanded our understanding of atomic science but also earned them Nobel Prizes. The discovery of radioactivity marked a turning point in physics, opening doors to new scientific possibilities. Radioactivity isn't just a single type of emission. In fact, there are three main types of radiation: alpha, beta, and gamma. Alpha particles are heavy and carry a positive charge, but they can be stopped by a sheet of paper. Beta particles are lighter, negatively charged, and can penetrate further, though a thin metal sheet can block them. Gamma rays, on the other hand, are highly energetic electromagnetic waves that require thick lead or concrete to shield against. Each type of radiation has unique properties and risks, making it essential to understand their differences for both safety and scientific applications. Let's take a closer look at alpha radiation. Alpha particles consist of two protons and two neutrons, making them relatively heavy and slow compared to other forms of radiation. Because of their size, alpha particles can't travel far and are easily stopped by skin or paper. However, if alpha-emitting materials are inhaled or ingested, they can cause serious internal damage. Alpha radiation is commonly found in elements like radium and polonium. Understanding alpha radiation helps us appreciate the importance of proper handling and safety measures when working with radioactive substances. Now let's talk about beta radiation. Beta particles are much lighter than alpha particles and can travel further through materials. They are either electrons or positrons emitted from the nucleus during radioactive decay. Beta radiation can penetrate skin and thin layers of metal, which means it poses a greater risk for external exposure compared to alpha particles. However, it's still less penetrating than gamma rays. Beta radiation is used in medical treatments and scientific research, but safety precautions are always necessary to minimize exposure. Gamma radiation is the most penetrating form of radiation. Unlike alpha and beta particles, gamma rays are electromagnetic waves with no mass or charge. They can pass through most materials, requiring dense substances like lead or concrete for effective shielding. Gamma radiation is often emitted alongside alpha or beta particles during radioactive decay. It's widely used in medical imaging, cancer treatment, and industrial inspection. However, due to its high energy, gamma radiation can be extremely hazardous if not properly controlled, making safety protocols essential in environments where it's present. Radioactive decay is the process by which unstable atomic nuclei lose energy by emitting radiation. This process is spontaneous and can't be influenced by external factors like temperature or pressure. Each radioactive element has a characteristic decay rate known as its half-life, which is the time it takes for half of the material to decay. The decay process transforms the original atom into a different element or isotope, releasing energy in the process. Understanding radioactive decay is fundamental to fields like nuclear physics, archaeology, and even medicine. The concept of half-life is central to understanding radioactivity. Half-life refers to the amount of time it takes for half of a radioactive substance to decay. This period can range from fractions of a second to millions of years, depending on the element. For example, carbon-14 has a half-life of about 5,700 years, making it useful for dating ancient artifacts. The predictable nature of half-life allows scientists to estimate the age of materials and track the decay of radioactive substances in various applications. Radioactivity isn't just a laboratory phenomenon, it's all around us in nature. Natural sources of radioactivity include elements like uranium, thorium, and radon, which are found in rocks, soil, and even the air we breathe. Cosmic rays from outer space also contribute to background radiation on Earth. While most natural radioactivity poses little risk, certain areas with high concentrations of radioactive materials can be hazardous. Understanding these natural sources helps us appreciate the balance between environmental exposure and safety. In addition to natural sources, radioactivity can be artificially produced in laboratories and nuclear reactors. Artificial radioactivity involves the creation of unstable isotopes through nuclear reactions, often for use in medicine, industry, or research. For example, technetium-99m is a man-made isotope widely used in medical imaging. Artificial radioactivity has expanded the range of applications for radioactive materials, but it also requires strict regulation and safety protocols to prevent harmful exposure. Radioactivity plays a vital role in modern medicine. Radioactive isotopes are used for diagnostic imaging, such as PET and SPECT scans, which help doctors visualize internal organs and detect diseases. In cancer treatment, targeted radiation therapy uses radioactive materials to destroy cancer cells while minimizing damage to healthy tissue. The use of radioactivity in medicine has revolutionized diagnostics and treatment, improving patient outcomes and saving countless lives. However, careful handling and safety measures are essential to protect both patients and healthcare workers. One of the most significant uses of radioactivity is in energy production. Nuclear power plants harness the energy released during radioactive decay, specifically through nuclear fission, to generate electricity. This process involves splitting the nuclei of heavy atoms like uranium, releasing vast amounts of energy. Nuclear energy provides a low-carbon alternative to fossil fuels, but it also raises concerns about radioactive waste and safety. Balancing the benefits and risks of nuclear power is a major challenge for modern society. Beyond medicine and energy, radioactivity has important industrial applications. Radioactive materials are used to inspect welds and metal structures for flaws, measure material thickness, and even sterilize medical equipment. These techniques rely on the penetrating power of radiation to provide accurate, non-destructive testing. Industrial uses of radioactivity have improved product quality and safety across many sectors, but they also require careful monitoring to prevent accidental exposure. Radioactivity has become an invaluable tool in archaeology. Techniques like radiocarbon dating use the predictable decay of carbon-14 to estimate the age of ancient artifacts and fossils. This method has revolutionized our understanding of human history, allowing scientists to date objects that are thousands of years old. The accuracy and reliability of radioactive dating have made it a cornerstone of archaeological research, providing insights into the past that were previously impossible to obtain. Space exploration has also benefited from radioactivity. Radioisotope thermoelectric generators, or RTGs, use the heat produced by radioactive decay to generate electricity for spacecraft. These devices have powered missions to distant planets, where solar energy is insufficient. The reliability and longevity of RTGs make them ideal for deep space missions, enabling humanity to explore the farthest reaches of our solar system. Radioactivity, therefore, plays a quiet but crucial role in our quest to understand the universe. While radioactivity has many beneficial uses, it also poses significant dangers. Exposure to high levels of radiation can damage living tissue, increase cancer risk, and cause acute radiation sickness. Accidents at nuclear facilities such as Chernobyl and Fukushima have highlighted the potential consequences of uncontrolled radioactive releases. Understanding the risks associated with radioactivity is essential for developing effective safety measures and protecting both people and the environment. Minimize the risks of radioactivity. Strict protection measures are in place. These include shielding, limiting exposure time, and maintaining distance from radioactive sources. Specialized equipment such as lead aprons and radiation detectors help monitor and reduce exposure. Training and regulations ensure that workers in nuclear facilities and medical settings follow best practices. By understanding and applying these safety measures, we can harness the benefits of radioactivity while minimizing its dangers. Detecting and measuring radiation is essential for safety and research. Instruments like Geiger counters, scintillation detectors, and dosimeters are used to monitor radiation levels in various environments. These tools help identify radioactive contamination, ensure compliance with safety standards, and guide emergency responses. Advances in detection technology have made it easier to track and manage radioactivity, protecting both workers and the public from potential harm. Managing radioactive waste is a major challenge for industries that use nuclear materials. Waste products from nuclear power plants, medical facilities, and research labs must be carefully stored and isolated to prevent environmental contamination. Methods include deep geological storage, secure containers, and long-term monitoring. Effective waste management is essential for protecting future generations and maintaining public trust in the safe use of radioactivity. Radioactivity can have significant environmental impacts if not properly managed. Accidental releases of radioactive materials can contaminate soil, water, and air, affecting ecosystems and human health. Long-lived isotopes can persist in the environment for thousands of years, making cleanup and remediation complex and costly. Understanding the environmental consequences of radioactivity is crucial for developing policies that balance the benefits of nuclear technology with the need for environmental protection. You might be surprised to learn that radioactivity is a part of everyday life. From smoke detectors in our homes to certain types of luminous watches, small amounts of radioactive materials are used in common products. Even the food we eat and the air we breathe contain trace amounts of natural radioactivity. While these levels are generally safe, understanding their presence helps us make informed decisions about safety and health. Radioactivity can also be found in the food we eat. Bananas, for example, contain potassium-40, a naturally occurring radioactive isotope. Other foods like nuts and potatoes also have trace amounts of radioactive elements. These levels are typically very low and pose no health risk. In some cases, food is intentionally irradiated to kill bacteria and extend shelf life, a process regulated to ensure safety. Understanding radioactivity in food helps dispel myths and promotes informed choices. Workplaces, such as hospitals, nuclear power plants, and research labs, require special precautions due to the presence of radioactive materials. Workers in these environments undergo regular training, wear protective gear, and use monitoring devices to ensure their safety. Strict regulations govern the handling, storage, and disposal of radioactive substances. By following these protocols, workplaces can minimize risks and maintain a safe environment for employees. Exposure to high levels of radiation can damage DNA, leading to genetic mutations. These mutations can increase the risk of cancer and other health problems, and in some cases be passed on to future generations. Research into the genetic effects of radioactivity has improved our understanding of how radiation interacts with living cells. This knowledge is vital for developing treatments and protective measures against radiation-induced genetic damage. Radioactivity is a double-edged sword when it comes to cancer. While high doses of radiation can cause cancer, controlled doses are used to treat it. Radiation therapy targets cancer cells with precise doses of radiation, destroying them while sparing healthy tissue as much as possible. Advances in technology have made radiation therapy more effective and safer, offering hope to millions of patients worldwide. Radioactivity has even found a place in the art world. Scientists use techniques like radiocarbon dating to authenticate ancient artworks and artifacts. By measuring the decay of radioactive isotopes in organic materials, experts can determine the age of paintings, sculptures, and other objects. This scientific approach helps museums and collectors verify the authenticity of valuable pieces, preserving cultural heritage for future generations. Agriculture has also benefited from radioactivity. Radioactive tracers are used to study plant growth, soil composition, and nutrient uptake. These techniques help farmers optimize crop yields and manage resources more efficiently. In addition, radiation is used to develop new plant varieties through mutation breeding, creating crops that are more resistant to disease and environmental stress. Environmental scientists use radioactivity to track pollution, study water movement, and monitor ecosystem health. Radioactive tracers can reveal how pollutants spread through soil and water, helping to identify sources of contamination. These insights are essential for developing effective environmental policies and protecting natural resources. Radioactivity, therefore, is a powerful tool for understanding and safeguarding our environment. Forensic scientists use radioactivity to solve crimes and identify remains. Techniques like neutron activation analysis can detect trace elements in evidence, linking suspects to crime scenes. Radioactive isotopes are also used to determine the time of death in forensic investigations. These methods have improved the accuracy and reliability of forensic science, helping to deliver justice and closure. Radioactivity remains a vital tool in scientific research. From studying the structure of atoms to exploring the origins of the universe, radioactive materials provide unique insights that are impossible to obtain otherwise. Researchers use radioisotopes to trace chemical reactions, study biological processes, and develop new technologies. The ongoing study of radioactivity continues to push the boundaries of human knowledge. Radioactivity is at the heart of nuclear weapons, which use uncontrolled nuclear reactions to release massive amounts of energy. The development and use of these weapons have had profound effects on global politics and security. The destructive power of nuclear weapons underscores the importance of international treaties and efforts to prevent their proliferation. Understanding the science behind these weapons is essential for informed discussions about peace and security. Nuclear accidents, such as those at Chernobyl and Fukushima, have highlighted the dangers of radioactivity when safety systems fail. These disasters released large amounts of radioactive materials into the environment, causing health problems and long-term contamination. Lessons learned from these events have led to improved safety standards and emergency response plans, but the risks associated with nuclear technology remain a serious concern. Public perception of radioactivity is often shaped by fear and misunderstanding. High-profile accidents and media coverage can create anxiety, even when risks are low. Education and transparent communication are key to building public trust and ensuring that the benefits of radioactivity are understood. By addressing misconceptions and providing accurate information, we can foster a more balanced view of this powerful force. Strict regulations govern the use, transport, and disposal of radioactive materials. National and international agencies set safety standards, monitor compliance, and enforce penalties for violations. These regulations are designed to protect people and the environment from the harmful effects of radiation. Ongoing research and technological advances continue to shape regulatory frameworks, ensuring that radioactivity is used safely and responsibly. Innovation in radioactivity has led to new technologies and applications. Advances in medical imaging, cancer treatment, and energy production are just a few examples. Researchers are exploring ways to make nuclear power safer and more efficient, while new detection methods improve our ability to monitor and manage radiation. The ongoing quest for innovation ensures that radioactivity continues to benefit society in diverse ways. Looking ahead, radioactivity may play a key role in the future of energy. Research into nuclear fusion, which powers the sun, aims to create a virtually limitless and clean energy source. While fusion technology is still in development, its potential to revolutionize energy production is immense. The safe and responsible use of radioactivity will be essential as we seek sustainable solutions to global energy challenges. Nuclear energy, powered by radioactivity, offers a low-carbon alternative to fossil fuels. As concerns about climate change grow, many countries are investing in nuclear power to reduce greenhouse gas emissions. However, debates continue over the risks and benefits of nuclear energy. Balancing energy needs with environmental protection is a complex challenge that will shape the future of radioactivity in society. Education is key to understanding and safely using radioactivity. Schools and universities teach the principles of nuclear physics, radiation safety, and the many applications of radioactivity. Public outreach programs and science museums help demystify radioactivity, making it accessible to people of all ages. By fostering scientific literacy, education empowers individuals to make informed decisions about radioactivity in their lives. International cooperation is essential for managing the risks and benefits of radioactivity. Organizations like the International Atomic Energy Agency, IAEA, promote the safe use of nuclear technology, facilitate information sharing, and support nonproliferation efforts. Collaborative research and global standards help ensure that radioactivity is used responsibly and for the benefit of all humanity. Use of radioactivity raises important ethical questions. Decisions about nuclear energy, medical treatments, and waste disposal involve weighing risks and benefits for individuals and society. Ethical considerations also arise in the development and use of nuclear weapons. Open dialogue and transparent decision-making are essential for addressing these complex issues and ensuring that radioactivity is used for the greater good. Some artists have used radioactivity as a theme or medium in their work. From sculptures that incorporate radioactive materials to paintings that explore the invisible world of radiation, art can offer unique perspectives on the impact of radioactivity. These creative expressions invite us to reflect on the scientific, social, and emotional dimensions of this powerful force. Radioactivity has captured the imagination of writers, filmmakers, and artists. From comic book superheroes to science fiction movies, radioactivity is often portrayed as a source of power or danger. While these stories can be entertaining, they sometimes exaggerate the risks or benefits of radioactivity. Understanding the real science behind the fiction helps us separate fact from fantasy. As technology advances, new challenges and opportunities arise in the field of radioactivity. Issues like radioactive waste disposal, nuclear security, and the development of fusion energy will require innovative solutions and international collaboration. By staying informed and engaged, we can help shape a future where radioactivity is used safely and responsibly for the benefit of all. Each of us has a role to play in ensuring the safe use of radioactivity. Whether it's following safety guidelines at work, making informed choices as consumers, or supporting responsible policies, our actions matter. By staying educated and aware, we can help prevent accidents and promote the positive uses of radioactivity in society. Summary: radioactivity is a powerful force that has transformed science, medicine, industry, and society. Its discovery opened new frontiers of knowledge and innovation, while also presenting significant challenges and risks. Understanding the science, respecting the dangers, and embracing the benefits, we can ensure that radioactivity continues to serve humanity in positive ways. The story of radioactivity is still being written, and its impact will be felt for generations to come.